the instruction. Okay, and once the operation is done, then the result is also stored back into the accumulator only. Okay, let us now discuss how direct addressing and indirect addressing is performed with a suitable example. Okay, here in this instruction format, one bit is additionally added, that is I bit field is additionally added in order to distinguish either the address part of the instruction specifies the direct address or indirect address. I bit, it is known as mode bit. Okay, if the mode bit is equal to 0, the address part of the instruction specifies the direct address. If I bit equal to 1, the address part of the instructions holds the address of the effective address. Okay, let us now discuss how it is implemented inside the basic computer in this example. Okay, here just to take this example, in this memory, both the instructions as well as operands are stored inside the same memory. Here you can see in the upper part of the memory, instructions are stored. In the bottom part of the memory, operands are stored. If we go to the memory location 22, we can find one instruction which contains 0 in the I bit field and add in the opcode part 457 in the address part. Okay, since I bit contains the value 0, it represents that the address part contains the direct address of the operand. Okay, so if the processor goes to this location, it can find out the operand. It can find out the operand. So now this addition operation can be performed by taking compulsorily one of the operand from accumulator and another operand from this memory. Okay, now this addition operation can be performed. This plus indicates the ALU operation. This ALU operation is performed by the ALU unit. Okay, after the addition operation, the result is going to be stored back into the accumulator only. Okay, whereas coming to this diagram here, whereas coming to this example, the instruction contains in the I bit it contains 1. So it means that the address part of the instruction contains the address of the effective address of operand. Okay, so if the browser goes to this address, it can find out the effective address. Okay, so what is effective address? The address where the operand is actually stored, that is known as effective address. So the browser, when it goes to this address, it can find out the effective address. If it goes to that effective address, it can find out the operand. Then by taking one of the operand from the accumulator and one operand from the memory, addition operation can be performed and the result is going to be back stored into the accumulator. Okay, let us now discuss about computer registers. Registers are the fastest and smallest storage units that resides inside the processor and are used by the processor for various purposes during the execution of the instructions. Okay, there are 8 different registers are available in basic computer. Those are program counter registers, address register, instruction register, temporary register, data register, accumulator, output register, and input register. Okay, let us now discuss what is the content stored in each and every register. Okay, coming to the data register, its size is 16 bit. Its size is 16 bit. It holds the operand read from the memory. Data register, it is used to hold the data that is read from the memory. Whereas coming to the address register, its size is 12 bit. Okay, it holds the addresses during memory operation. Okay, what operation can be performed in memory? Either read operation or write operation. Okay, memory words can be read or written. Okay, either the memory words are read or written. During each and every memory operation, the address register should hold the address of the memory word that is written or read from the memory. Okay. Whereas coming to the accumulator, it is known as the processor register. It holds one of the operand required for ALU operation, and after performing the ALU operation, the result is also going to be stored back into the accumulator. Its size is 16-bit. Okay. Coming to the instruction register that holds the instruction that is read from the memory. Its size is also 16-bit because it is also one of the memory word, right? So memory word size is 16-bit. Whereas coming to the program counter register, it holds the address of the next instruction to be executed in the program. Okay, since it holds the address, the register that hold the address, it is of size 12-bit only. Okay, whereas coming to the temporary register, it holds the temporary results or intermediate values which are generated during the processing of instructions. Okay, its size is 16-bit. Whereas coming to the input register, it holds input character read from an input device and its size is 8-bit. Coming to the output register, it holds the output character to be sent to an output device. Its size is 8-bit. Let us now discuss common bus system. Common bus system, it provides communication path to transfer information from one register to another and between memory and registers. Okay. The main advantage of using common bus system is that it avoids excessive use of wires, particularly when the computer is designed with multiple registers. Okay, here you can observe a common bus. Here this common bus, it connects 8 registers and 1 memory unit. Okay, this common bus is constructed using three input multiplexer. This common bus is constructed with 3 input multiplexer, and the size of the common bus, that is, it can carry 16-bit information over the bus. Okay. Coming to the connection of a register to the common bus, out of 8 registers, only 6 registers output are connected to the bus. That is, out of 8 registers, only 6 registers can transmit information over the bus. Okay, the two registers, input registers and the output register, these two cannot pass, it never passes any information over the bus, because input register, it sends its information to the ALU unit only, and the output register, it always sends its information to the output device only. Okay, whereas coming to the register that receives information that is passed over the bus. Okay, out of 8 registers, uh, only 6 registers can receive information that is passed over the bus. The two register, accumulator and input register, they never receive information that is passed over the bus directly. Okay. Here you see input register, it always receives information from the input unit only, and accumulator, it always receives any information through the ALU unit only. Okay, so accumulator, it never receives directly any information from the bus. Okay, so this is the connection between the registers to the common bus. Let us now discuss the very important point in common bus system, that is, out of 6 register and memory unit, who has to transfer its information over the bus, and when the information is passed over the bus, out of a 6 register and 1 memory unit, who has to receive the information. Okay, that point is very important. Okay, register who has to receive the who has to transfer its information over the bus, is it is determined based on the selection signals of the bus. Okay, here you can notice in the common bus system the numbers are present along the each register and memory unit. These numbers are the decimal equivalent of the binary values of selection signals. If suppose the selection signals values are 001, then the address register has to transfer its information. Okay, and if suppose the selection signal values are 010, then program counter register has to transfer its information. Okay, so similarly, the other registers also need to transfer its information only based on the selection signal values. Okay, coming to the memory unit, then it can transfer its information. Okay, for this also selection signal values must be equivalent to triple one. Then only the memory unit can transfer its information over the bus. In addition to that, the read signal of the memory also need to be enabled. Okay, so in addition to selection signal, read signal of the memory unit also must be enabled. Then only the memory unit can transfer its information over the bus. Okay, just assume that one of the has transferred its information over the bus and it is passed via the bus. Now, who has to receive the information? It is determined by enabling the load signal of the register if it has to be received by one of the register, and if it has to be received by the memory unit, then write signal of the memory unit has to be enabled. Okay. So using selection signals and load signal of the register and read and write signal of the memory unit, who has to transfer and who has to receive the information over the bus is determined. Okay, values are 001. What is the number equivalent to 001? It is 4. Okay, the selection signal values are 001. The accumulator has to transmit the information because 001 is equivalent to the number 4, right? Okay, so now the accumulator need to transmit the information over the bus. Okay, and whenever the information is passed over the bus, who has to receive the information? That is determined by enabling the load signal of the registers. You can observe, except the input register, all the registers are having load signal because they can receive, except accumulator, all the other registers can receive the information, whereas accumulator also receives the information from the ALU unit. Okay, the register who has to receive the information that is passed over the bus is determined by enabling the load signal of the register. Okay, so only two important point, that is, who has to transmit the information is determined by setting the selection signal values. If suppose address register has to transfer the information over the bus, what is the number for this? 1. Okay, so for this the binary value has to be 100. If the selection signal values are 100, by this time address register has to transmit the information. So then who has to receive the information? That is determined by enabling the load signal of the corresponding register. If suppose load signal of the PC program counter is enabled, then this register will receive the information that is passed over the bus. Okay. Let us take one more example. For example, if memory unit has to transfer the information, okay, then by the time the selection signal values must be triple one, because the number which is specified along memory unit is 7, right? So for that the binary values need to be triple one. Okay. So for this memory unit, if it has to transmit the information over the bus, in addition to the selection signals, its read signal also must be active. Its read signal also must be active. Okay. So this is the point about memory unit. It has to be remembered. Okay, for memory unit, in addition to the selection signal, its read signal also must be active. Then only the memory unit will transfer the information over the bus. Okay. And for then if memory unit has to receive the information, by the time write signal of this memory unit must be active. Write signal of the memory unit is active, but for the registers its load signal need to be active. um, if we take one register transfer a statement, that is address register to the program counter. Address register to the program counter. If this transfer has to be achieved, what should be the selection signal values? Because address register, it has the number 1, right? So the selection signal values must be 100. So when selection signal values are 100, then address register can transmit its information, and the load signal of the program counter need to be activated. If this is done, the transfer will be done successfully. Okay. Let us now discuss a different category of computer instruction formats. Okay. The computer instructions can be classified into three categories. One is a memory reference instruction, a register reference instruction, and a IO instructions. Okay. All the three category of instructions are of size 16-bit only. Okay. How these classifications are made, let us now discuss. If 12 to 14 bit of the instruction, that is opcode part, are not set to triple one, okay, then it can be of type memory reference. Okay, and if 12 to 14 bit of the instructions are equivalent to triple one, then it can be register reference or IO operation. When it is equivalent to triple one, it can be register reference or IO instruction. The either register or IO instruction, how can we determine? Based on the I bit value. If 15th bit is equivalent to 0, then it is known as register reference, and if it is equivalent to 1, then it is known as IO. Okay. Whereas coming to the memory reference instruction, the 12 to 14 bit, that is opcode values, are never be equivalent to triple one. And we can also again classify the memory reference instruction based on the address part of the instruction. Um, okay. Either it contains direct address or indirect address, that is based on the I bit value. If I is set to 0, then the address part contains the direct address, and if I is set to 1, then the address part contains the indirect address. Like this, the instructions in the basic computer can be categorized into three types. Let us now discuss what are the different operations are supported in each category. Coming to the memory reference instructions, as we just discussed, the memory reference instructions are identified if a code part of the instruction do not contain triple one. Okay, in such case, it may contain these combination of values only. It may contain 000 to 110. Okay, if triple zero values there in the opcode part, then the operation to be performed is and memory word to accumulator. If the opcode part contains 001, the operation to be performed is and memory word to accumulator. So like this, based on the opcode value only, the corresponding operation is performed. So totally 7 operations are specified by memory reference instructions. Okay, then based on the I bit value, if I equal to 0, the address part of the instruction specifies the direct address. If I equal to 1, then the address part specifies the indirect address. Students, you can observe here 12-bit binary code of the memory reference instructions are specified. If you observe here, this is for the direct address memory reference instruction. This part is for um, indirect address memory reference instruction. Here in this 15th bit, you can observe in all the instructions it is set to 0 and the output field are set to 000 to up to 110. Okay, coming to the indirect address memory reference instruction, the 15th bit, all the 15th bit are set to 1. The output part contains the 00 up to 000 up to 110. Okay, so in both the category, you can observe when it is 000, then the operation to be performed is AND. Okay, when it is 001 in both the category, the operation to be performed is add memory word to accumulator. Okay, when it is 010, load accumulator from memory. When it is 011, store content of accumulator into memory. When it is 100, branch unconditionally. 101, branch and save return address. 110, increment and skip if 0. Okay, the only difference between these two instructions are the address part. When it is having 0 in the 15th bit, the address part of the instruction, it holds the direct address, and when it is holding 1 in the 15th bit value, the address part contains the indirect address. That is the only difference. Okay, here you can see in the address part we have not specified any of the binary value, because it is not possible to specify the exact address in any of the instruction, right? So that's why the x values are included here. Okay, it represents one of the address. Okay, it can be any one of the address. Here, hexadecimal equivalent values of these binary code are represented. Usually, whenever we discuss about instruction code and memory addresses, we use hexadecimal code only because it is compact and easy to understand and discuss also. Anyhow, this binary code, if it is written, you can understand the concept very clearly. That's why I have taken the binary code as an example to explain the memory reference instructions. Let us now discuss about register reference instructions. The register reference instructions are identified if 12 to 15th bit of the instruction contains 0 1 1. Okay. Then what is the operation to be performed is specified in the 0 to 12 bit of the instruction. Okay, students, once again I repeat, in register reference instructions, the 0 to in register reference instructions, the bit values in 12 to 15 bits are specially only used for identifying the type of the instruction. Only used for identifying the type of the instruction. If it is 0 1 1, it is known as register reference instruction. But exactly what operation to be performed, it is determined based on the um, register operation that is specified in 0 to 11 bit of the instruction. Okay, here you can see in all the instructions, the 12 to 15th bit of the instructions are having 0 1 1 values. Coming to the 0 to 11 bit portion, you can see in each and every operation, only one bit of the 12 bits are set. One bit in the one bit out of the 12 bits are set. In this 11th bit is set. In this 10th bit is set. Here 9th, here 8th. So it is here 0th bit is set. Okay. When 11th bit is set, the operation to be performed is clear accumulator. When 10th bit is set, clear extended accumulator bit. Then accordingly, the complement extended bit, then circulate right accumulator and extended accumulator bit, circulate left accumulator and E, increment accumulator, skip next instruction if accumulator is positive, skip next instruction if accumulator is negative, skip next instruction if accumulator is 0, skip next instruction if E is 0, halt accumulator like this. 12 different operations are specified in register reference instructions. Okay, let us now discuss IO instructions. In IO instructions, all the instructions are having one binary value in 12 to 15th bit. Okay, 12 to 15th bit values are having one binary value. You can see in all the IO instructions, okay, they are having one binary value in 12 to 15th bit. Okay, whereas coming to the 0 to 11 bit portion, as we just discussed in register reference, any one of the bit out of 12 bits will be set. Okay, here you can see the 11th bit is set here, 10th bit here, 9th. So accordingly, in IO instructions, 6 different IO operations can be specified. When 11th bit is set, what is the IO operation need to be performed? Input character to accumulator. And when 10th bit is set, output character from accumulator. Accordingly, for 9th, 8th, 7th, 6th, skip on input flag, skip on output flag, interrupt on, interrupt off. Like the 6 different IO operations are supported in basic computer. Let us now discuss whether the instruction set of the basic computer is complete or not. The instruction set of the computer is said to be complete if it includes a sufficient number of instructions in each of these four following categories. Okay, one is arithmetic, logical, and shift instructions, and instructions for moving information to and from memory and processor registers, and program control instructions together with instructions that check status conditions, then IO instructions. And if each of these categories, if the instruction set of the computer includes sufficient number of instruction, then that instruction set is said to be complete. Okay, let us now discuss whether the instruction set of the basic computer is complete or not. Okay, coming to the basic instruction set of the basic computer, in arithmetic and logical and shift instruction category, the instructions that perform add memory word to accumulator, complement accumulator, increment accumulator, circulate right accumulator and extended accumulator bit, circulate left accumulator and E bit, and memory word to accumulator, complement accumulator. So with all these instructions that with the instruction that performs all these operations, arithmetic, logical, and shift operations can be achieved. Okay, the all the instruction which performs these operations comes under this category. Okay, whereas coming to the second category, the instructions that perform load memory word to accumulator, store content of accumulator to memory, these instructions come under second category. So these are used for moving information to and from memory and processor register, right? So these two instructions that perform LD and STA operations comes under this category. Okay, whereas coming to the third category, the instructions that perform the operations such as branch unconditionally, branch and save return address, increment and skip if 0, as well as uh, skip next instruction if accumulator is positive, skip next instruction if accumulator is negative, skip next instruction if accumulator is 0, skip next instruction if E bit is 0. So all these instructions are used to achieve program sequencing and control operations. Okay, the instructions which perform these branch operations and skip operations are coming under this program control instructions. Whereas coming to the fourth category, the instructions that perform input character accumulator and output character from accumulator, these two, the instructions which performs these two operations comes under this category, input output instruction. Okay, since the basic computer includes sufficient number of instructions under each of these four categories, then its instruction set is said to be complete. Okay, since in the basic computer instruction set there are totally 25 instructions are available, whereas 7 instructions are in memory reference, 15 instructions are in register reference, and 6 instructions are in IO instructions. So totally 25 instructions are available in the instruction set of the basic computer. Okay. So with all these 25 instructions, the operations that falls under these following 4 categories can be performed. That's why the instruction set of the basic computer is said to be complete. However, the frequently performed operations such as subtract, multiply, or XOR, these operations cannot be performed efficiently. Okay, but however, with the instructions available in the instruction set of the computer, these operations can be performed not that efficiently. Okay. Let us now discuss the control unit of a computer. The control unit is the one of the important components of a processor that interprets program instructions and generates control signals in order to direct other parts of the computer to perform specific micro operations required to execute those instructions. Okay, the important function of control unit is to generate control signals. So this is the very important function of control unit. Its only function of um, control unit is that generating control signals. Okay, through control signals only it direct other parts of the computer to perform required micro operations. Okay, there are two type of control units are there. One is hardwired control unit, another one is microprogrammed control unit. In this lecture, we are going to discuss about hardwired control unit. Okay, here in this figure, the block diagram of the hardwired control unit is illustrated. Here, the control unit is constructed with five important components. That is two decoders. That is 3 by 8 decoder and 4 by 16 decoder. One 4-bit sequence counter, one I flip flop, and control logic gates. Okay. So with these five components, a hardwired control unit can be designed. Okay. Um, just let us now discuss how this control unit decodes the instruction, and after that how it generates the control signals. Let us discuss now. Okay, whenever an instruction is read from the memory, it is placed in the instruction register, right? So in this instruction, the 12 to 14 bit of the that is opcode part of the instructions are received by the 3 by 8 decoder, and based on the opcode values, this 3 by 8 decoder, it will activate only one output line out of its 8 output lines. Okay, this opcode bits are 3 bits, right? So this opcode values can be um, anything in this range 000 up to 111. Okay, it's decimal equivalents of 0 1 up to 7, right? So whenever the input to the 3 by 8 decoder are 001, so its decimal equivalent is 0, right? At the time it will activate the output line designated with T0. Okay. Similarly, if suppose if the input to the decoder is a 111, then its decimal equivalent is 7, right? So that then it will activate the output line designated with D7. Okay. Then 15th bit of the instruction will be received by the I flip flop. The 15th bit, it can be 0 or 1, whatever it may be, that will be forwarded to the control logic gates. And coming to the 0 to 11th bit, that will be sent to the control logic gate as it is without any decoding. Okay, coming to the 4-bit sequence counter, its function is to count the numbers from 0 to 15 in binary form. 0 to 15 in binary form. Okay, once it reaches 15, again it will restart from 0 to, and it will continue its counting process. Okay, whatever the numbers it generates in binary form, those are given as input to the 4 by 16 decoder, based on which it will this 4 by 16 decoder, it generates the timing signals. Okay, if the output generated by 4-bit sequence counter are 0000, then its decimal equivalent is 0, right? So then this 4 by 16 decoder, it will activate the timing signal T naught. And if the input given to the 4 by 16 decoder are 0001, it's equivalent to the decimal number 1, right? So then it will activate the timing signal T1. Okay. So accordingly, for each and every clock cycle, whenever the 4-bit sequence counter um, it counts the numbers in incremental order, the 4 by 16 decoder also, it will generate the timing signal in incremental order. Okay, so when the clear input of the 4-bit sequence counter is active, then the 4 by 16 decoder, it will activate T naught timing signal. Okay, so these are the important functionalities of the components of hardwired control unit. Okay, so here you can notice the outputs from the 3 by 8 decoder and 4 by 16 decoder and I flip flop on 0 to 11 bits of the instruction. All these are received by the control logic gate, and after that this control signals are generated by the control unit in order to direct the other parts of the computer to perform the required micro operations according to the instructions fetched in the instruction register. Okay, let us now discuss the relationship between the control signal and timing signal. Okay, as we just discussed, timing signals are generated by 4-bit sequence counter and 4 by 16 decoder, right? So 4-bit sequence counter, it will count the number from 0 to 15 in binary form. So according to the output of the sequence counter, the 4-bit 4 by 16 decoder also, it generates the timing signal T naught up to T15. Okay, so whenever freshly the T naught timing signal need to be generated, the 4-bit sequence counter need to be cleared. Okay, clear input of the sequence counter must be set. Okay, so this is the concept just now we discussed. Here, just look at the timing diagram. In this timing diagram, whenever the instruction execution starts, the clear input of the sequence counter must be active. Here you can see it is in the rising edge. Okay, so it is active. So whenever it is active, in the 0th clock cycle, T naught is active. T naught is active. Okay, and in the subsequent clock cycles, you can observe the sequence counter clear input is not active. It means the sequence counter its increment it can perform it can count the numbers in incremental order from 0 to 15. Okay, so in this clock cycle it will count to 0. So by the time T naught is active, in the next clock cycle it will count to 1. By the time in the next clock cycle T1 is active, in the next clock cycle T2 is active, it goes on. Okay, if suppose if there is a requirement like whenever D3 and T4 are enabled, then if sequence counter need to be cleared, then how it can be achieved? How it can be achieved? Once again, I repeat, if D3 and T4 are active, then by the time if sequence counter need to be cleared, how it can be represented in the timing diagram? Okay, you see here when D3 is active, assume that D3 is active during third clock cycle, during the third clock cycle, and when T4 is active during the fourth clock cycle. So during this point, both the signals are active. So at that time, sequence counter need to be cleared, right? So let us represent the sequence counter is also cleared at this point in time. The clear input of the sequence counter, it goes to the rising edge. Okay, so you can observe in the next clock cycle, the timing signal generated is T naught. Okay, T naught is active. Okay, so how it can be explained in the block diagram of the control unit. So when D3 is active from this decoder and T4 is active from this decoder, and when both these signals are active, immediately the control unit activates the clear input of the sequence counter. This is what the meaning, and it can be represented in timing diagram like this. Let us now discuss the instruction cycle of an instruction. In a basic computer, when a machine instruction is executed, it goes through the four phases in its instruction cycle. In the first phase, the instruction is fetched from the memory. In the next phase, it is decoded. In the third phase, the effective address of the operand is read from the memory if the instruction has an indirect address. And this phase is applicable only to the memory reference instructions and is not applicable to register reference and IO instructions. Okay, and after that the instruction is executed. Okay, these four phases are repeated for executing each and every instruction in the program until the halt instruction is encountered. Let us now discuss how what are the micro operations are performed during fetch and decode phases of an instruction cycle. Okay, let us take this illustration. Just assume that a program is loaded into the memory whose first instruction is stored into the memory address 255 and whose halt instruction is stored into the memory address 300. Okay, so before starting the instruction cycle of the first instruction stored in the program, few initialization need to be done. What are those initializations? The program counter must be loaded with the address of the first instruction in the memory, and the sequence counter need to be cleared. This sequence counter need to be cleared in order to generate timing signal T naught in the next clock cycle. That's why this program counter and sequence counter need to be initialized before starting the instruction cycle of the first instruction in the memory. Okay, so just if these two initializations are done, the fetch, the micro operations required to perform the fetch phase of an instruction cycle can be started. Okay, just before going to discuss about the micro operations, let us have a look on the common bus system. This common bus system, it illustrates the selective portion of the common bus system, what we discussed just now. Okay, here this common bus system, it illustrates how the timing signals are connected to the bus, memory unit and registers which are required to perform the fetch phase of an instruction cycle. Okay, um, just coming to the first clock cycle immediately after the initialization of the immediately after the initialization, uh, a T naught will be active, right? The T naught timing signal will be active. So by that time, in order to transfer the content from program counter to address register, it can be achieved by setting the selection signal values 0, 1, 0 because program counter is having the number 2, right? So what's the binary equivalent of the what is the binary equivalent of this number 2? 0, 1, 0. Okay, so by setting the selection signal value 0, 1, 0, the content can be transferred from program counter and can be passed over the bus, and to receive this information by the address register, the load signal its load signal must be activated. Okay, so by enabling T naught and selection signal values as 0, 1, 0 and by enabling load signal, this micro operation, that is data transfer from program counter to address register, can be achieved. Okay, here why this transfer has to be done, that is very important point, because address register is the only register that is directly connected with the memory unit. Okay, so whenever a memory operation is performed, that memory word's address must be loaded into the address register. Okay, so when its address is available in the address register, then only that particular memory word can be read or written. Okay, so keeping the memory address of the memory word into the address register, that is very important before doing any memory operation in the memory unit. Okay, so after this, after transferring the address of the instruction from program counter to address register, now next clock cycle will be activated, right? So during that time, what micro operation need to be done? Let us discuss now. Okay, when timing signal T1 is active, right now the address register is holding the address of the first instruction because it was transferred from program counter, right? So now it is holding 255. So now from this particular address, the instruction can be read and it can be loaded into the instruction register. Okay, how this transfer from memory to instruction register can be performed? What is the micro operation required? Okay, to transfer the instruction from the memory and from the memory location that is available in the address register to instruction register, it can be achieved. How it can be achieved? If the selection signal values are set to 111 and its read signal is active and the load signal of the instruction register or instruction is enabled, then this micro operation can be achieved. Okay. In addition to this micro operation, one more operation also performed. What is that? Program counter value is incremented by 1. How it is achieved? By enabling the increment input of the program counter. Okay, and why this program counter need to be incremented? Because it has to point to the address of the next instruction in the sequence, right? So that's why it has to be incremented during the timing signal T1 of any instruction. Okay, so by this time when it is incremented, it will be holding the memory address 256, which is the address of the next instruction in the sequence. Okay, the micro operations which are performed during T0 and T1 are related to the fetch phase of an instruction cycle. Okay. So by executing this micro operation, now the instruction will be available in the instruction register, right? So during the next during the next clock cycle, timing signal T2 will be active. During that time, the instruction need to be decoded. The fetch instruction from the memory, it has to be decoded by the control unit. How it is decoded, let us now discuss. The opcode part of the instruction, that is 12 to 14 bit of the instruction, need to be decoded by the 3 by 8 decoder. Once it is decoded, it will activate the output lines of D0 to D7. Any one of the output line will be active. Okay, then 0 to 11 bits of the instruction is sent to the address register, and 15th bit of the instruction register is sent to the I flip flop. So like this, decode decode phase of an instruction cycle is performed. Okay. So after performing the decode phase of an instruction cycle, um, in the next phase, it has to be executed if it is IO or register reference instruction, and if it is memory reference instruction, the effective address of the operand need to be read, right? So it depends on the type of the instruction. What is the um, next phase to be performed? Okay, so it is very important to determine what is the type of the instruction. Okay, here in this flow chart you can observe the micro operations what we discussed during the timing signal T0 and T1. That is during the fetch phase of an instruction cycle, what are the micro operations are performed, and during the decode phase of an instruction cycle, that is during timing signal T2, how a decode is performed, just now we discussed, right? So after this, okay, the D7 D7 output of the decoder is verified. If D7 is equivalent to 1, then the instruction can be of type either IO or register reference. Okay, and either it is IO or register reference, it depends on the I bit value. Okay, if I is equivalent to 1, it is of type IO instruction, and if I equal to 0, it is of type register reference. And this is ensured during the timing signal T3, and once it is ensured, the corresponding IO instruction or register reference instruction is executed. Okay, at the end, the sequence counter also must be cleared. Okay, whereas coming to the other side of D7, if D7 is equivalent to 0, when D7 will be equivalent to 0, when the opcode part is not equivalent to 111, that is when it holds the values between 0, 0, 0 up to 110. Okay, so when opcode part is not equivalent to 1, then it can be of type memory reference. Either the address part of the instruction contains direct address or indirect address. It depends on the I bit value. If I bit value is equivalent to 1, then the effective address of the operand need to be read from the memory and it has to be loaded into the address register. Okay, and this is performed during the timing signal T3, and if the address part contains the direct address of the operand, nothing is done during the timing signal T3. Okay, and in the next timing signal, when T4 is generated, the corresponding memory reference instruction is executed. Okay, and at the end, the sequence counter also need to be cleared. Here, the micro operations what we discussed in order to determine the type of the instruction are illustrated here. That is, when D7 is equal to 0, I value is 1 during the timing signal T3. What is the micro operation to be done? The effective address of the operand need to be read from the memory, and it has to be loaded into the address register. Okay, so to achieve this, what signals need to be active? The selection signal values must be triple one. The then a read signal of the memory also need to be active. Okay, to receive the information that is passed by the um, bus, it has to be received right by the address register. Then its load signal also must be active. Okay, so by enabling these signals, this transfer from memory to address register can be achieved. Okay, when D7 is 0 and I equal to 0 during the timing signal T3, nothing is performed. Okay, when D7 equal to 1, I equal to 0, and during the timing signal T3, the register reference instruction is executed. Okay, when D7 is 1 and I equal to 1, and during the timing signal T3, then IO instruction is executed. Okay, um, like this, micro operations are performed during the different phases of an instruction cycle. Students, if you find this video useful to you, kindly subscribe this channel. Thanks for watching.